What's up, guys? I've been trying to do this a couple times, and every time I try writing on it, it's for some reason not working. So I'm just going to kind of go through the notes for you real quick, without writing, just kind of so you can kind of see what everything kind of means. So optimization problems, kind of five big things that we look at. We look at minimizing or maximizing the slope, finding the maximum or minimum distance of a function, or like a point to a function. We've kind of looked at that before. Finding the maximum volume of something based on knowing different things like the radius and certain things like that. Finding the minimum surface area is kind of a good thing to look at as well, or maximum surface area, and then minimum or maximum profits. But kind of like these ones, like minimum slope, maximum distance, maximum volume, minimum surface area, max profit, are kind of the five most frequently asked questions. Probably maximum or minimum distance are probably the first two big ones. And then maximizing or minimizing a specific area or volume are kind of the next kind of things that we look at. So what a question would look like for you guys, you at least know, so if you have some function f of x and we know that we're looking at on a specific function, how can we minimize the slope? Well, all you do is if you just derive it and you find out when is the slope the smallest, well, that's minimizing the slope. So you would just kind of look at it that type of sense. We've done that in the past. It's a very kind of simple one. That we look at. So like when is the slope 0, or does it go further into negatives or something of that sort? Here's a very common question. Find the minimum distance from any point on y is equal to x squared minus 2x plus 5 to the point 4 comma 0. So the point 4 comma 0 is not on this graph, but it is, we're looking at what's the minimum distance from that point to the graph. So the way to do it is the first thing we want to do is similar to that of a related rates question. We want to find out what type of static relationship do we know. Well, we know the distance formula. And from the distance formula, we can use our x and y, x1, y1 to be 4 comma 0. And then we also know that f of x is equal to x squared minus 2x plus 5. So if in the place of x sub 2, we can put in x, and in the place of y sub 2, we can put in x squared minus 2x plus 5. So if you have that, now we have a specific distance formula. If you multiply it through, we can derive it. If you look at deriving it and looking, because what we're looking for is the minimum volume. So we have this equation where now if we're looking at the derivative of the distance in terms of x, we can find that, set it equal to 0, and find out the minimum points. So if you go through and you solve it, you get 1.326. You get to be the critical point of this function. And so it goes from decreasing to increasing at 1.326. So since it's decreasing and increasing, we know it's a minimum. So of this distance formula, the minimum, or the smallest distance from any point there, that from 4 comma 0 to any point on this graph, is going to be what you get, that 1.326. So if you kind of look at that, that would be kind of the certain value that you can go through and actually solve and kind of find out what that distance would be. Another type of question, find the dimensions of a rectangle with the largest area that has its base on the x-axis and its other two vertices above the x-axis are on y is equal to 8 minus x squared. So if you kind of draw out this picture, we have this specific, let me see if this actually works. I don't have to rewrite this, but you never know, might work. So we have this area right here, this base, and then so we can create different areas looking at this, just looking at certain rectangles and figuring out which one is the largest. So we want to maximize it. Okay, so we want to maximize our rectangle. So we're maximizing the area of this, which is L times W. Well, what's the length going to be? Whatever our x value is here, we get 2 of x is going to be our length, and our width is going to be just whatever our y value is there. So if you have the area is equal to 2x times y, well, if we know that y is equal to 8 minus x squared, we can plug that in. Now we have an area where if we look at the derivative of the area with respect to how x works, we can find the maximum value of what that x is going to be. So if we look at it and we plug in, you get 4 over the square root of 6. If you want to find out what that area is, you just plug in 4 over root 6 for x. You have to multiply it by 2 in order to get going to the left and the right of it, and you can find out what that specific area is. And another very common type of problem is, say if we have a barn and we have we know how much fencing we have. So we say we have 500 feet of fencing. And what we want to do off this barn, we want to build a specific area, and using what we know about perimeter and what we know about area, we can combine those two to figure out, what's the maximum amount of area, this X times Y. So how we can do that is we can find the specific constraint. We know that X plus 2Y is equal to our perimeter because we don't have to put fencing on this side over here because that's the barn. So we know what the perimeter is going to be, and we know how much fencing we have. So we know that X plus 2Y is equal to 500. So if you solve for that, you can plug it into this area equation. And so instead of X plus 2Y is equal to 500, you can make it X is equal to 500 minus 2Y, plug that into X here. And now we have area in terms of X, and we can, or Y, I guess here's Y, and we can go through and figure out what our Y value would be. And then once you find out what your Y value would be, you know what your X value would have to be. And then using that, we can find out our area. So it's just kind of cool different ways to be able to go through and find and look at certain optimization problems. Another one, we have 1,600 centimeters squared in material available to make an open top box with a square base. Find the largest possible volume of the box. So we know that the volume is going to be the length times width times height. So if we know what the surface area has to be as well, it's a box. So this one's a little bit different than the one that you guys did because there is a top as well to it. So this is kind of how you would go about doing that. We have a specific surface area. We have the constraints. We know what the length and the width is. We know the area is of A is L squared. We know that that B is L times H, and we can go through and use all those to get everything in terms of L. So if you get everything in terms of L, you can look at the volume with respect to the L, and then you can find the maximum or minimum by just deriving it in terms, in this case, I think we divide it in terms of L, so dVdL, which is right here. And if we look at dVdL, you can go through and find the maximum volume of this specific box, which I think we got at 6,158. So just kind of go through these. I know they might be a little bit messed up. I wish I could have, every time I try writing too much on it, it doesn't save. So and I think that's it for the first set of notes. So those are just a couple different types of optimization problems. So remember, the first thing that you're kind of doing is you're looking for a specific equation that you can use. So whether it's using the distance equation or it's using the certain equations, like in this case, we knew what the volume was, so length times width times height. We knew what the surface area of it was just by looking at adding together these sides. We can use those specific equations to put them together in terms of we want to find the largest possible volume of the box. So that's the equation that we're using in the end. And we want to be able to plug everything into. So in this case, we found what W and we found what H was in terms of L. And being able to do that got a volume right here in terms of everything in terms of L, so that then we can derive it and maximize out what the L is. So it's just kind of using these different types of ways to be able to solve it. So if you guys have any questions on this first set of notes, please let me know. Hopefully I just talked through that pretty well. I'm going to try and fix this for next time that I do notes and to be able to write on it and maybe get a different program or use a different computer. So, but other than that, you guys should be all set and good to go. If you have any questions, please let me know. Send me an email. We can do a Google Hangout as well to kind of go through and help you out. So other than that, you guys have a good day and stay healthy.